This meeting is being recorded.
In this next video from chapter 17 on some additional aspects of aqueous equilibria, we're going to start here with acid-base titrations that you're most familiar with. By that, I mean strong acid, strong base. So that's what we'll take a look at in sample exercise 7. But I just wanted to quickly review some of the information provided here about acid-base titrations. So we see the apparatus here, the setup that's commonly used, where we have our stir plate here with a stir bar inside of our beaker. Notice that we have an unknown concentration. This could be either acid, as we see here, or base. And then we have up top here in our burette, we have, in this case, a base here, sodium hydroxide, with a known concentration that we're going to titrate against our hydrochloric acid of unknown concentration. So either or could be an acid or a base, but whatever our titrant is, the stuff that we're titrating into the beaker, that has to be the known concentration, because we'll measure our starting volume and then our final volume. We'll find the amount used, and we'll use that in a calculation. So once we reach this equivalence point, so this term right here in bold, this means that we have an equivalent amount. So the stoichiometric amounts of acid are equal to base. So we have moles of acid equal moles of base at this equivalence point. So volume can be calculated using the molarity, the known concentration of the solution, times volume that we dispensed, will give us moles. Because if you remember, molarity is measured in moles per liter. And then when we multiply by our volume in liters, these will cancel out, and then we'll end up with our amount of moles to reach our equivalence point. So that's what we're going to do in sample exercise 7. But before we head there, just take a quick peek here at this graph. This shows a pH of 7 exactly at our equivalence point. So again, this is probably the type of titration you're most familiar with when we have a strong acid titrating a strong base, or vice versa. Our equivalence point will be exactly at 7. So pH equals 7 at the equivalence point. We're going to see that if we titrate a weak acid with a strong base, or vice versa, we're going to get, in the first case, a higher than 7 equivalence point, maybe around 9 or 10. Again, that's a weak acid, strong base scenario. And then we would see the opposite with a strong acid titrating a weak base. So as we work through some examples, you'll see why that makes sense. So let's look at these key pointers here. We start the titration near the equivalence point. So we add some of our titrant, and we see that our pH goes up slowly. So that's our first point down here, where from the start, we near the equivalence point. Then just before and after, the pH will be increasing rapidly. So we could say this is our equivalence point, the start, and then right here is the end. So we're rising in between. And then at the equivalence point, we already know that moles of acid equal moles of base. We're going to use that below. And then as more base is added, the pH tends to level off. So we would take multiple readings here, and we would add a few milliliters at a time, and we would create this type of titration curve. So let's take a look at sample exercise 7 here. So we're told that a student performs a titration. They have, to reach the end point, we needed 25 milliliters of sodium hydroxide, and this neutralized 24 milliliters of a 0.105 molar hydrochloric acid. So in this scenario, we're going to utilize this equation here that you might be familiar with, M1V1 equals M2V2. And we can plug in to solve for our moles of hydrochloric acid that are needed to reach our equivalence point. And then from there, we can determine the molarity of our sodium hydroxide in our solution by dividing by our total volume. So let's see what we have here. So again, our molarity of our sodium hydroxide will be our final calculation. But first, we have to use this equation here. So moles of HCl, we could find them if we rearranged this equation here, and we just utilized half of it. So let's see what that looks like. We would say that we needed 0.24 liters in our beaker, 24 milliliters of this 0.105 molar sodium hydroxide or HCl. This is our acid. So we're multiplying liters times moles per liter, and we see that we have 0.00252 moles. And we know that this is in a volume of 0.025 liters to reach our endpoint here. So this is our volume. So we're going to take this value, we'll make this equal to 0.00252 moles, and then we're going to divide by this, convert it to liters, 0.025 liters. So our final answer here is that our concentration, or the molarity specifically, of the sodium hydroxide solution is 0.101 molar, rounding to 3 significant figures.